Direct variation. Direct variation is another phrase that we're going to explain and try and figure out what it means. This is an example of faucet leaks. The volume of water wasted and the times when the volume was measured are shown. And the first thing it's asking you to do is graph the data. So here's a graph. Please remember that if you come to the time first on the left-hand column, then time should go along the bottom axis of your graph. So time should be on the horizontal axis, and that's in seconds, and volume on the vertical axis, and that's in milliliters. Okay, what I do know is that it has to go up to 50. So I could count by tens, maybe every second space, so I'm going to put 0. Every second space could be 10, let's say. So 10, 20, 30, 40, 50, 60 we could go to. Okay, and then up the side, our values have to go up to 80 or 75. So up the side, maybe I'll count the same way because that'll fit as well. So maybe every second line is 10, 20, 30, 40, 50, 60, 70, 80. 0, 0 is our first ordered pair. The second one, over 10, up 15. So over 10, up 15 would be there. And then 20, 30 would be here. 30, 45, 40, 60 here. 50, 75 would be up here. So what is created? We get a straight line from this graph. This information gives us a straight line. So when I follow the straight line up and draw a nice straight line, what I can see is this line passes through 0, 0. And what that means, that's a pretty important thing to notice. If the line passes through 0, 0, that ordered pair is also in the table. So that means after 0 seconds, 0 water was wasted. And that makes sense. If time hasn't even started to pass, then the water wouldn't have been wasted yet. So what we call this direct variation. Basically, that means when there is a straight line and the line passes through 0, 0, this graph is called direct variation. Okay? You can imagine that other graphs might not go through 0, 0, and they will not be called direct variation. So just the phrase direct variation is for lines that pass through the origin. When we go back and look at the questions, determine the rate of change and what does the rate of change represent? If we go back to the graph and we try and figure out what the rate of change is, rate, remember, is rise over run. So I could pick 2 points. It doesn't matter what 2 points I pick. And I want to look at rise over run. Let's look at maybe this point here and this point here. If we choose points that aren't too far apart, that might make it easier for us. The numbers will be smaller that we're working with, and maybe that would be easier. So first I need to decide what the rise is. So vertically, from 30 to 15, that is a rise of 15. And horizontally, from 10 to 20, that is a run of 10. Okay, the change from 10 to 20 is 10. So we end up getting a rate in that way, and the rate is rise over run. So that would be 15 over 10, rise over run. So if we go back to the questions at the top, rate is 15 over 10. Rate equals rise over run, and that is 15 over 10. What I actually get is 1.5. The next part is asking, what does a rate of change represent? Well, what does 1.5 represent? Remember our table talked about milliliters per second. So 1.5 milliliters is wasted every second. Then it asks you to write an equation for this relation. We've started to kind of look at rates and how an equation would look with a rate in it. So for example, the volume of water. Usually it's the right side of the graph. We're going to talk about volume. The volume of the water is equal to the rate with a variable beside it. So the rate is 1.5 milliliters. And the variable beside it could be time, or it could be S for seconds. Maybe I'll use a T. So what that means is every 10 seconds, 1.5 would be multiplied by 10. And that's how I would get 15. Every 20 seconds, 1.5 milliliters is wasted every second. So 1.5 times 20 would give me 30. Okay, so the rate with a letter beside it, that's how you write equations. Volume equals 1.5 T is an equation for this relation. And then it says, determine the volume of water wasted after 100 seconds. Well, writing equations helps us because now all we need to do is sub in the 100 for T. So determine the volume of water wasted. The volume is 1.5 times the time. And this time it's 100 seconds. And 1.5 times 100 is 150 milliliters. So 150 milliliters would be wasted after 100 seconds. Okay, and then how much would be wasted after 3 hours? Well, 3 hours, you have to figure out how many seconds that is. 3 hours. Okay, that's kind of tricky. All right, I know that there's 60 minutes in an hour, and I know that there's 60 seconds in a minute. A quick way to do this would be to figure out how many seconds are in 3 hours. So I could take 60 seconds times 60 minutes times 3 hours, and I get 10,800. So there's 10,800 seconds in 3 hours. Then if I wanted to figure out the volume of water wasted, V equals 1.5 T. So V equals 1.5 times 10,800. And when I multiply those two numbers together, I get 16,200. So that's quite a bit. It's 16,200 milliliters is a lot. If you imagine a skinny carton of milk would be 1,000 milliliters because that's 1 liter of milk. So imagine 16 skinny cartons of milk. That's how much in 3 hours you've actually wasted if you have a leaky tap that is leaking at a rate of 1.5 milliliters per second. So just to sum up on the back here of your page, it says the previous graph is a straight line that passes through the origin 0, 0. This illustrates direct variation. Direct variation passes through 0. That's what you really have to remember. When two quantities vary directly, they are proportional. So that means we are going to be getting a straight line. The cost is directly proportional to the mass, as an example. We write equations for direct variation in the form y equals mx. So usually you'll be able to figure out a rate. Okay, you'll be able to figure out a rate, and the rate is the m. So the equation that we just did was y equals 1.5 t. I don't care if it's an x or a t or what kind of variable it is, as long as the rate has a variable beside it. Because that variable means that's where we would sub in the time. If it's 30 seconds, 100 seconds, 500 seconds, it doesn't matter. We would sub it in for time. So it's 1.5 is the rate times the time. So that's how all of the equations are going to look. For direct variation, they all look the same. So as a last example here, it says, which graphs represent direct variation? This, I'm hoping you'll think, is maybe the easiest question you've ever seen. The line has to go through 0, 0. So this is not direct variation, but this one is, right? Because the line passes through 0, 0. And then down below, this one here is a line that passes through 0, 0. So that is direct variation. And then the last example, the height of a ball. I know this starts at 0, 0. That is where this curve starts. But this is not a line. So we would say it's not direct variation because it is a curve and not a straight line.